As a reminder, you've already dealt with inverse trig functions in the past. Back in geometry, you've had to do problems like this, where you can set up the equation using SOHCAHTOA. So this is the sine of theta equals 8 over 14, or theta equals inverse sine of 8 over 14 to the nearest degree. What does that mean? How do I, oh, calculator, right. So you pull out your calculator, make sure it's in degrees mode and not radians mode, and you type in the inverse sine of 8 divided by 14, and you get 34.8499, blah, 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 which is approximately equal to 34, it says to the nearest degree, so 34.8 actually goes up to 35 degrees. And that's what theta is approximately. Same with the other ones. We do, let's see, this is tangent of theta equals 13 over 5. Oh, you thought that might be a 5, 12, 13 right triangle, but curveball, it's not. Anyway, tangent of theta means theta equals the inverse tangent of 13/5. Once again, we go to the calculator. And we do tan of 13 over 5 equals approximately 69 degrees. Okay, and then one last time. We probably have a cosine here, right? Yeah, adjacent over hypotenuse, so cosine of theta equals 36 over hypotenuse 54. Cosine equals theta equals inverse cosine of 36 over 54. And rinse and repeat. 48 degrees. Alright, that's kind of boring, but check out this. We all see screens that are large and broadcast onto walls, right? We want to be able to see the largest viewing angle possible so we can see the best we can possibly see. So we're going to try to optimize that distance D so that I've got as big a viewing window as possible. Okay, so we've got person in the chair, eye level 4 feet high, looking at this screen that is 30 feet high, but it's not at eye level. It's 8 feet from the floor, just like the woman is 4 feet from the floor. So we're going to try to figure out how big is this angle right here, not the entire angle, which would go all the way down to here. That's actually already got a name. That's called theta 2. And then theta 1 is this itty bitty angle here. So let's put it out here to make it more clear. We're looking for this angle right here. Don't go into that unshaded region. Stay inside the blue region. Okay? That's our answer. So note that there are 2 right triangles in the diagram above. We're going to use one of the triangles to create an equation with D and theta 1. D and theta 1. Well, that's that really skinny triangle right here. It's hard to draw, it's so skinny. It's got a right angle in there, so it's SOHCAHTOA that we're talking about here. And we can see that theta 1 is opposite 4 feet. Let's draw that a little bit more clear. This is my skinny angle theta 1, and this is a distance of D. Where did this 4 come from? It says 8 here, but it says 4 right here. Well, the 4 came from 8 minus 4. Okay, so that's going to give us the top half of that distance. So anyway, we've got ourselves a tangent problem. Tangent of theta 1 equals 4 over D. Let's see, that's a right angle. Don't forget about that. And then do the same thing with theta 2. This time we're using the entire side from here all the way up to here. Not 32 feet, not 40 feet, but 32 plus 4, or 36 feet. Okay? So we've got the tangent of theta 2, that great big angle that's too big, equals 20. Nope, I subtracted. I just said 36. 36 over D. SOHCAHTOA. 2 equations above. Use an inverse trig function to solve for each angle. So theta 1 equals the inverse tangent of 4 over D. And theta 2 equals the inverse tangent of 36 over D. All right, note that the viewing angle V, it's not labeled in the diagram, but we'll label this V for viewing angle, is the difference between theta 2 and theta 1. Theta 2 is big, theta 1 is small. V is the difference between them. Write an equation for V in terms of D. Well, we were just told that V equals the difference between theta 2 minus theta 1. So we're subtracting, and we know what theta 2 is, and we know what theta 1 is. We've got inverse tangent 36 over D is theta 2 minus inverse tangent of 4 over D. Inverse tangent of 4 over D. All right, so that's what V equals. V, the thing we're looking for, is this expression right here. We like it because the only variable on that side is D, which is what we're trying to, remember D is this value right here, right? And we're trying to make that as good as possible. So we're going to try to make this value as good as possible when V is as big as possible. So we're going to use a graphing calculator to take a look at this graph. So I'm going to pause this for a second. I got my calculator in hand. This time I'm just going to use Desmos so you guys can see what's going on. But graph in whatever you want to graph in our function, which is the inverse tangent, or arctan, of 36 over D, but I'm going to graph it, so I'm going to call my D value X, because we don't have a D axis, it's an X axis, minus arctan of 4 over D, and we get, X, and we get ourselves a graph. Now let's make sure we understand what this graph is showing us. The input value X represents, in this problem, it represents D, the distance the chair is from the wall. And as D changes, as D changes, it affects the size of our viewing angle. So that will be our vertical axis. So, for example, the point 3.61, 0.642 means when D equals 3.68, V, remember that's the viewing angle, equals 0.642. So I copied this into here so I could draw on it, and we are talking about a D-axis now, where that's the distance between the chair and the wall, and everything's measured in feet, so this is measured in feet. All the distances are measured in feet, and the viewing angle, well, that's kind of strange. What does that mean to have a, what was that, 0.62 or something really small? That's a tiny angle, isn't it? Oh, wait. Tiny angle because we're not talking about degrees. We're talking about radians. Radians are going to be your default mode to graph in, but in this case, I think we'd probably rather our answer be in degrees, so we're going to change our mode. So we're going to, we can do that in any calculator we want to, but the way you do it in Desmos is you click on the wrench and you change that from radians to degrees. That dramatically changed the scale here because just in the x-axis, because degrees are so much smaller than radians. So we're going to zoom out, and I'll pinch this together and zoom out some, and it's still going up. So we're going to pinch some more. Aha! There's some information. This is the shape of the graph. And what do we care about? Well, they told us what we cared about. Let's go back and reread the question. It said, if my computer will cooperate, which it won't. I think I got it working again, but at any rate, this was the viewing angle axis measured in radians, which we decided we didn't want radians. So we changed the mode to degrees, and we zoomed out, digress, degress, degrees. And then we didn't change the horizontal axis. That's still our distance D that we're after in feet. And notice that what we're interested in is what is the maximum viewing angle, and that boils down to that maximum point right there, which any calculator can do for you. On Desmos, you simply click on the function you want, and then click on the point you want. 12, 53.13. 12, 12, 53.13, I believe. Remember that the input is my d value, and my output is my v value, measured in degrees. So what is the optimal distance? Well, the optimal distance to maximize the viewing angle is 12 feet. That maximum value is 53.13, but it happens at a d value of 12.